Hello, my name is Aiden, and I'm working with Eric and Cassandra for this project, and we are doing problem one, the turntable problem. For this problem, we're taking into consideration how to solve a real-world context problem for this course. And if we look at the understand and plan portion of the problem, we can see three main components of this problem. We have the understanding the problem, so we're going to identify relevant quantities, appropriate symbols, and numbers in case there are any. And we're going to identify our assumptions as well. So any simplifications or any assumptions that we can make for this problem to make it easy to solve, or any reasonable assumptions that we can make for this problem as well. And the last part is representing the situation physically. So it's just making a diagram or a graph that might help you solve the problem, and you're identifying your values and your givens as well. Okay, so first, let's make sure we understand this problem and put the problem in our own words. So for this problem, we have a box on the edge of a turntable, and it's rotating at constant angular speed. So we're given that it's rotating at a constant angular speed. The spring passing over the pulley and through a hole in the table connects the box to a hollow ball with the string wrapped around the ball many times, and we're asked to determine the angular speed of the turntable. Okay, and so we're provided this visual as well, so we can look at that and maybe it'll give us more context to our problem. So now we're going to identify our assumptions and account for the values that were given in this problem. This was just the problem in our own words, but in the prompt we are given some things as well. So here's some assumptions that we have. So for this problem, we know that the turntable is frictionless. It states in the problem. We know that the pulley is massless as well, and that the ball is hollow, and we're going to assume that the ball is a perfect sphere as well. So when we assume that the ball is a perfect sphere and the ball is hollow, we need to account for that when we're doing the solving part of this problem, because it's important for the moment of inertia, because the moment of inertia for a hollow sphere is different than that of a solid sphere. And another assumption we can make, the system is rotating at a constant angular speed, like there's nothing that's going to change it. That's a given thing as well, but it's still an assumption that we can make. And another assumption is that the spring is ideal. So there's certain constraints to that that will be important in solving the problem as well. Some given values that we have is that the mass of the box on the edge of the turntable has mass of capital M. The radius of the turntable is going to be capital R, and the mass of the ball is little m, the hollow ball, and the radius of that ball is R. And then we also know that the string is wrapped around the ball many times. And so that could just change something with the effective radius of the ball as well. So that's just something that we should take into account as our given values. Okay, now that we've identified our assumptions, we can go back to that solving a real world context problem and look at the physical aspects of this problem. And so we can represent the problem physically with a model. And so we created this model, pretty simple, but we identified some given values as well as contextualized more of the physical aspects of this model. And that is such as like the location of the spring, how it passes over the pulley, and the spring would be kind of in the middle here, or going through this turntable as well. And so that we can see with this constant W that I wrote, that we know that this is going at a constant angular speed in one direction. We have our box on the edge. We have an identification of this radius going to the center of the turntable from the edge of the turntable. We know our pulley is located in the center, but this pulley is massless, as we said before, so it's not going to affect necessarily the spin of this because it's moving constantly. And we have our ideal spring, and then we have our string and our hollow ball as well. And we identified the radius of that ball attached to it, and I tried to make it seem like the ball is the string is wrapped around the ball many times as well. So that was just a simplification and a better way to contextualize this problem with this model to make it simpler for understanding what is the physical aspects of this model, which it asks us to do so. And then we'll go on to the calculation portion of this problem as well. So thank you.
All right, so for this problem, we have a ball rotating in the system. So we're going to have to consider torque equations, moments of inertia, and rotational motion. First thing we're going to do is just consider the equations that we are likely to need. So we're going to need, of course, the second law anytime we do a force. We're going to need centripetal acceleration. We're going to need angular acceleration. We're going to need our torque equations as well. And we're going to need a moment of inertia for our ball. So what we can do is we can set up different force equations for both the box and the ball. For the box, all there is to consider is the tension force. And using our Newton's second law, F equals ma, we're able to use the mass of the box, big M, times centripetal acceleration, which is centripetal, of course, because it's connected to a rotating ball. And then using our equation for centripetal acceleration centripetal acceleration equals angular velocity squared times r. We're going to sub that in. Next, we can consider the force in the ball. And the ball has two relevant forces. It has a tension force and a gravitational force going in opposite directions, hence why there's opposite signs. So we have the tension force minus the gravitational force equals mass times acceleration. Next, we have torque. And our theta in this situation is just going to be 90 degrees, and sine of 90 degrees is 1. So we can just simplify this to R times F for torque. We can also use this moment times angular acceleration equals RF. And then keep in mind that we know that angular acceleration would be centripetal acceleration over R. So we can sub this in and set this as an expression for the ball's torque as well. We also know that for later use, that the ball's moment of inertia is going to be 2/3 mr squared. And this is the moment of inertia from the table for a hollow sphere, which is what we have in the problem. So next, we just have to set up our equations and use known terms to plug things in and eventually isolate angular velocity and get angular speed from that. So our first expression, this ft minus fg over m over r, that actually comes from our earlier expression for the force in the ball, which is the tension minus gravity equals ma. All we did was solve for a and plug it in there to our equation for Newton's second law. And then the 2/3 mr squared, of course, is the moment of inertia for the ball. And from that point, it just turns into algebra. We're going to solve for tension. And then we know from earlier that tension is equal to big M times omega squared big R. And we're going to be able to get our omega into the equations. And at this point, the omega is going to be the only unknown, and we can solve for it and get everything in an expression of omega, which is what we want. So finally, we have omega, or angular velocity, is equal to the square root of 2/5 mass times gravity over big M, big R. And of course, this is going to be an absolute value because the question or the problem asks for angular speed, not velocity. Speed is going to be a magnitude of velocity. Next, we just have to make sure all the units check out. So we're just going to square everything to get rid of the square root. And then we're going to make sure that our kilograms cancel, which they do, and our meters cancel. And then we're left with a constant over seconds squared is equal to omega squared. And keep in mind that omega squared is angular velocity or angular speed, and the units for this is radians over seconds, and radians is unitless. So we would expect to just have some constant over seconds in the denominator for our final answer. And that's what we get when we do this cancellation. And of course, we take the square root of omega again and the square root of seconds again, and it gives us some constant over seconds, which is proper because it can be thought of as radians over seconds for our angular speed. Finally, we can make sense by just using some covariational reasoning. We can see how increasing little m can increase our angular speed, which makes a lot more sense because if the little m is more significant, it will contribute a lot more to what's happening in the system. And the moment of inertia will increase due to this as well. And since our angular velocity is related to moment of inertia, then that means that this would also increase.
For the reflection portion of our presentation, we've chosen to include 2 examples from past homework assignments to show the similarities between them. Our first example we took from homework 3. This problem contains a pulley system that we needed to find the acceleration of. Now, when we solved this problem for the homework, we needed to be able to understand how the 2 masses acted upon each other because they're tied together by a string. Once we understood how these forces were acting on each other, we could use that to understand how they were acting on the pulley itself. Understanding these 2 pieces brought us to our end goal of finding the acceleration of the system as a whole. This set us up to be able to solve our project problem. It's related because we needed to understand how the pulley system sitting on the turntable was acting on itself so that we can understand how that might act on the turntable. For our second problem, we've taken a problem from homework 4, which features a rotating disc. This project problem that we chose is based on finding the angular speed of a turntable, so this example relates perfectly. To solve this homework problem, we use the moments of different parts of the disc as well as the brick that was being placed onto it. The connections here are that the disc acts as the turntable in our problem, while the added brick acts as the pulley system. This was a helpful problem because when presented with this project, we already knew that this problem would need to understand how to solve for angular speed when a rotating object has a separate mass sitting on top of its surface. Thank you.